Okay, it's time to reach the conclusion of session 35. This has been a really important session, very long. So it is worthwhile to spend the final 10 minutes of our conversation just browsing back at the main ideas that we've developed. As we said, the main purpose of this session is to have the complete toolkit that we will need for session 36, where we will be building a generalized calculator for derivatives, mostly options and credit-related derivatives. So our toolbox started with the moment-generating function and characteristic functions of stable density functions. So we explore mostly how to write the code in Maple in order to start with a random variable, to obtain the moment generating function, and then to extract from the moment generating function the corresponding momenta. In section 2.2, we moved in the direction of characteristic functions. We saw that characteristic functions bear an important resemblance with Fourier transforms. We started with the normal distribution and we ended up writing the code and obtaining the corresponding characteristic functions. We compare the calculation step by step with the direct application of the Maple command. Now we put together a set of graphing interfaces that allows us to see, for instance, how the characteristic function changes for a normal distribution with different parameters. We did the same with a uniform, non-centered uniform distribution, where we will change, or we can change the parameters just clicking the plot function, and then obtain the results in the complex space. This is the corresponding characteristic function of a centered uniform density. Now, we continued forward and tried to use the concept of a characteristic function for stable variables, and reaching, by simple observation of the characteristic function plot, a generalization of the central limit theorem. A calculator allows us to see how the characteristic function of a normal and the characteristic function of the average of an arbitrary function could eventually converge. So here we're repeating what we did in chapter 2, but in complex space, and we see more clearly the convergence of a normal, which is the dotted blue, and the characteristic function of the average of samples obtained out of a uniform distribution. Now, we looked at some of the characteristics of stable random variables. Essentially is the first concept that approaches the notion of affinity, which is a linear combination or some sort of combination of random variables which produces a random variable with the same distribution. We started from the definition and we saw and we developed a visualizer where on the right hand side we had the linear combination random variables, and on the left hand side we tried to find a value of C and D that could make this characteristic function equal to this one. So for instance, here we have the addition of two identically distributed random variables, which in this case are normal. We see that these can be reproduced and producing the same characteristic function if we put C equal to 2 and D equal to 0. We noticed and developed this application for different distributions: the Pareto, the uniform, and the normal. We moved in the direction of a more specific definition of what we believe we understand by stable distributions and how they can be parameterized. This will prove to be extremely useful from the point of view of intuition when we approach the concept of affine distributions. Then we reached something that is absolutely central and perhaps one of the most beautiful results that we have in modern finance. It's clear that it is very hard in many cases to obtain closed form solutions directly working with densities, especially for complex derivatives. However, if we move into complex space and we work with the Fourier transforms of the densities and the Fourier transforms of the rules that are used for calculating the derivative, then we can reach closed form solutions in that space. And then by applying an inverse Fourier transform, we can get the corresponding values of the option in the state space. So this moves us in the direction of not so much obsessing in working with simple distributions in state space, but working with simple distributions in Fourier space, and then coming back to state space. So the situation in which we can have a relatively simple definition of a characteristic function comes with the notion of affine processes. And in this exercise, what we did is that in the end, a derivative is some sort of the application of an operator on a characteristic function. So if that operator is relatively simple and very standardized, and then we plug in a characteristic function, then we will have the characteristic function of the derivative, and then we walk back using inverse Fourier transforms. So we work with, we can actually notice that we can split the problem in two halves. One half is about finding the characteristic function of the stochastic process, and the other half is building the operator that will act on it, and that will depend on the characteristics of the specific derivative. We went to the simplest possible case of building a solution in Fourier space for the standard coloption. Then we moved in the Black-Scholes framework. Then we got a little bit more adventurous and did the same exercise for the variance gamma model. So here it is, and we built a calculator to see how this behaves in Fourier space and how this behaves in the state space. Naturally, the next challenge is how to move from the Fourier transform or the characteristic function back to state space using the inverse Fourier transform. And at that point, we stress the fact that numerical methods will be of extreme use, not just because they are fast, but because they can be applied very easily. So here we presented a case on how to work from the Fourier space back to the state space using the fast Fourier transform algorithm of Maple. And we took a look at the error of these FFT and the IFFT models. So we saw in these graphs the difference between the FFT and the inverse, the original Z variable, and the inverse FFT of an FFT of Z. Now, we will need to work with Riccati equations eventually when we deal with affine processes. So we took a look at how to set up and resolve Riccati equations. And finally, we moved to our affine processes. We built calculators following Duffy's, Penn, and Singleton papers for general basic affine diffusions. So here's our calculator. In this part, we have the moment generating function, and here we calculated our function and our characteristic function. So we will continue next class. Thank you for staying. and see you soon.